Swayam Prabha. Digital India. Educated India.
The simple strategy is look at any vertex and look at the chains which are ending at it, right. Many chains may be ending at it, not just one chain, many chains may be ending at it. Longest chain ending at it, ending at vertex V, ask how many vertices are there in this chain, and that cardinality, that number, use it as a color, that number use it as a color and give that color to that vertex. This is the algorithm which I am proposing, and so every vertex will get a color now, right. But the question is it a proper coloring or not? So you have given a color to this, that is not enough, right. Okay, if it was just a matter of giving color, I could have given some color to every vertex, right. But you have to make sure that it is a proper vertex coloring. So to check whether it is proper vertex coloring or not, what should I do? I just have to take an edge, so UV edge, and see whether U and V are getting different colors, right. But I know the rule by which I assign colors to this. So I considered all the chains which are reaching U, and the number of vertices in the longest chain was given as a color to U, and the number of vertices in the longest chain reaching V was those, let us say L of E, L of U, right, was given as a color to this. Is it possible that L of E is equal to L of U? That is my question, because if it is equal, then it is not a proper coloring, no. If it is not equal, we are okay. What is the argument that it can never be equal? So the thing is, suppose it is same, that is the way you should tell. Suppose it is same, then what happens? Suppose, so let us say the direction from U to V is like this. It can be the other way also without loss of generality. Now you know, suppose this is the longest chain which is reaching U. L of U is the number of vertices in it. Now of course this can be attached with it, and here L of U has to be at least L of U plus 1, right, in fact greater than or equal to 1. So how can it be equal? So there is a longer chain ending at it, right. So it never be equal. That is a tricky one line statement, but it works, right. So that coloring strategy seems to give you a proper vertex coloring. And now the number of colors you have used is what? Maximum number of colors you have used is, so some vertex might have got the biggest color, no. That means the chain is ending at that vertex with those many vertices. But then there is a clique. If there is a chain of that length, then that chain will correspond to a clique, because a chain means the transitive relation makes it a clique, because it is, though we imagine the chain as a path, but then you remember there is a transitive relation. That means if there is a path, there all possible edges are there, right, because I to j there is somehow I can reach, then transitivity makes that I to j edge also, right. So finally, so therefore that is it. So this tells us that chi perfection is there. All induced subgraph or comparability graph, same arguments works there. Is the alpha perfection here. First we should know what is alpha here. Alpha means independent set, right, the biggest cardinality independent set. So in the partial order literature, interestingly there is another word used for independent set. What is the word? It is called anti-chain. Somehow maybe these were not developed at the same time, maybe different people developed this, so they use the word. It is not surprising that they use the word anti-chain, because you can see that chain was a clique, right. So anti-chain was the independent set there, right. So, so anti-chain means a collection of vertices somewhere in the partial order such that no two of them are comparable. It is exactly the independent set, there is no need to describe it too much. So it is independent set, right. And So, biggest cardinality of an anti-chain is what we are concerned about when we are talking about alpha of G, and our interest is to prove that alpha of G is equal to clique cover number. Clique cover number means how many cliques are required to cover all the vertices. You remember it's like the chromatic number, but on the complement we see that, right, the cliques to cover. But we have already seen that these cliques corresponds to what? Chains, right? Cliques means chains, right? Total orders. Chains are total orders, right? Now, the number of chains so that all the vertices are covered, that means every vertex goes to exactly one of the chains. The number of total orders so that every vertex of the partial order goes into one of them. The number of total orders required to cover the partial order. Okay. What is that? Number of chains required to cover the partial order. You can easily see that it has to be at least the anti-chain, because a chain cannot take two vertices from the anti-chain, because in a chain any two vertices has to be related with each other, right, because that's what, no? It's a total order. So, therefore, at least as much as anti-chain, but the famous theorem from Dilworth, have you studied that? Dilworth's theorem is called. It says that the total orders required, the number of total orders required, minimum number of total orders required to cover the partial order is equal to the maximum cardinality of an anti-chain, right. So, essentially that is what we are looking for, right. You can prove it to yourself, but I will leave it at that, because that also an older theorem, so will come from. So, that is because probably these things were the fascination when Burge looked at this perfect graphs initially. He saw that many of these theorems, so you should recall that it is in 1960s or something like that, right. So, at that time he might have found all these things very fascinating, right. So, all these theorems are becoming alpha chi perfection or alpha perfection in some subclass of graphs. So, it was definitely worth studying the perfect graph then, right. So, we have covered comparability graph to some extent. I hope you remember what it is at least. So, always associate comparability graphs with partial orders, and I just covered alpha perfection and chi perfection there to give some idea, and then connect to perfect graph literature. And recall now to know that comparability graphs are perfect. We do not need any of these things, because now the strong perfect graph theorem is known, it is proved, right. So, what does strong perfect graph theorem says? It says you just have to look whether there is a odd Hall or an odd anti-Hall. Odd means at least 5, right, odd 3 is not considered among them. So, Hall of length 5, 7, 9 etc., or anti-Hall of. You can quickly see that halls are not there, right. We have already seen that odd cycles cannot be transitively oriented, right, but anti-halls you have to check. That is, I will give it to you as an exercise. It's a quick check whether can you transitively orient anti-halls. That means the complement of halls, is it possible to get it from a partial order. That means, is it possible to orient the edges of it? It will be a contradiction somehow, just check it out, right. So, that way also we could have come up with the perfection. So, we do not have to go through all these things now, but then because the strong perfect graph theorem is proved already, right, that is a very heavy theorem, right. So, now let me see. So, I think because we will it may be a good idea to cover some more classes. Yeah, so I will just mention some other classes also. Another very subclass of comparability graphs which is familiar, but only a subclass of comparability graphs. So, take an interval graph and take the complement of that. What do you mean by that? In interval graph, if an edge is if there is an edge, then just remove that edge, and if there is no edge, put that edge, right, complement, right. Whenever there are two vertices are not connected in the interval graph, then put the edge, otherwise don't. This is called the co-interval graph. Co-interval graph because it is the complement of interval graphs. Any graph G is a co-interval graph if G complement is an interval graph. Can you see that this is a natural comparability graph? Very natural comparability graph. This is the partial orders, a partial order is associated with that, not the such partial orders are called interval orders and all, right. There are a lot of literature in that. So, very natural simple partial order is associated with that. Can you see that? That is a question. So, you have to visualize it, there is no point telling. So, think of an interval graph, an interval representation, and now imagine what would be the complement of that. That means, whenever interval graph has an edge, whenever two intervals intersect, right. So, in the complement an edge is there when they do not intersect, right. When they do not intersect, two intervals do not intersect on the real line, what can you see? What order is there between them? There is an order, right. One interval comes before the other interval, that is it, right, is not it? There is a natural order there. For instance, if this is an interval and if another interval is not intersecting with this, it should be either like this after this or it should be before this, right. So, whenever two intervals are not intersecting, one is after or left or right of it, therefore, there is a natural order in this increasing way. So, there is we can say that one is greater than the other, but if it is intersecting, it is difficult to tell, right, because you will start telling with respect to the start points and all, but then it is possible that something is inside and all kinds of confusions will be there, but you can try to cook up orders there, but it will be more complicated. But here no complication, it is very simple, right, because they are not intersecting, one should be above or below that, right of it, completely right of it or completely before it. So, if you take the complement of interval graph, they do give an order whenever there is no edge between two vertices, there is an order, and that means in the complement, when there is an edge, you see a direction given, and the only thing you have to verify is transitivity is there or not. Naturally, it is there, right, because if A is related to B, suppose this is A, this is B, so and then B is related to C, that means C is above C. So, C is after B, right. This is in the sequential, right, one after the other coming. So, this is only a partial order, this is not a total order, because still we have those things in the interval graphs where intervals were not intersecting, right. So, they do not have that order between them, right. So, so therefore, it is only a partial order, right. So, these are interval orders. So, therefore, so what we say is that interval graphs are co-comparability graphs, we will say, mean complements of comparability graph, only a subclass of co-comparability graphs, co-comparability graphs, we will say. Not all co-comparability graphs are interval graphs, but all interval graphs are co-comparability graphs, complements of comparability. So, now let me move to another class of graphs called split graphs. So, very simple class of graphs is a subclass of caudal graphs. Subclass of caudal graphs. If it is a subclass of caudal graphs, then it is a perfect graphs anyway, right. So, how does a split graph look like? It is split, it can be split into an independent set and a clique. That is the split graph. That means the vertex set can be partitioned into two groups. One will be an independent set. How many is unimportant? One will be an independent set. The other will be a clique here. That means something like this. All edges will be here, and there can be any kind of connection between this and this. Here, this connection is, there is no control over that. But there is nothing inside this portion. This is a stable set, independent set. This every edge is there here. This is a clique. This is okay. So such kind of graphs are called split graphs. And why do I think that split graphs are caudal graphs? Because we cannot have any 4 or more cycles there. Can you see that quickly? Suppose there is a 4 cycle, what may be 4 or more cycle there? What? See, you cannot have a cycle like this. No, odd cycle will not come like this, because if I do like this, then it will be even cycle, right? Zigzagging. Go there, come back, go there, come back. Then if you want to close, it will be an even cycle. But if it is an odd cycle, some edge, right, somewhere we should also maybe something like this. We should move like this. Even this thing, so this is also not possible, because there are codes for all those things, right? Because do you see that cycles, why cycles are not possible? So because how many, in a cycle, a vertex can have only left neighbor and right neighbor, right? Other than if it does not have code. And suppose there is a vertex from the clique side, right? I told that split graphs have one independent set side and a clique side, and suppose I take a vertex from the clique side in the cycle, then I cannot have both its left neighbor and right neighbor here, right? Because then this edge will become a chord, right? Right. So therefore, one of them will go out, and then this is the only thing which I can have, but then there is no edge here. So how will I complete it, right? So think about it. Try to prove that there is no 4 cycle or more here, induced 4 cycle or more. But there is much easier way to see that it is caudal graph if you want to use our tools which we develop. For instance, can you quickly see a PEO here? PEO, perfect elimination ordering here. So for instance, you can do something like V1, V2, Vk, and then Vk plus 1 up to Vn. This can be the clique. You can enumerate the clique vertices in the later part and the independent set vertices in the first part. Do you see that this is a PEO? Because anyway, when you go from here to here, because that was a full clique. From here onwards, the neighbors are only in the clique. So anyway, neighbors will be clique, right? So there are various ways to see that this is a caudal graph, and if it's a caudal graph, yes, it is. Let's see. I'll do as much as possible. See this is also, you can take it halfway and take it as homework later. This is interesting. The split graphs are interestingly not only caudal graphs, they are also so called co-caudal graphs. What do you mean by co-caudal graphs? You are seeing this co word many times today. A complement of caudal graphs. Very easy to see. Why? Because if you take a split graph, so this was the split graph, right? So edges here. Now take the complement of this graph. How will it look like? It will look like this will become clique, right? And this will become independent set, and these edges may change. Something else may come. Something else may come, right? Something else means what was not there in the earlier will come. So therefore, the split graphs, if you take the complement, is again a split graph, neatly the same structure, right? So if the original was a caudal graph, the complement is also a caudal graph. So, it is actually the complement of a caudal graph. The original was a complement of a caudal graph. It is caudal graph and complement of a caudal graph, right. So, in other words, a split graph is caudal graph and a co-caudal graph. Right, because its complement is also caudal, so it can be seen as the complement of a caudal. But that itself is not the interesting part. So, the converse is also correct. What is the converse? That means, if you are given a graph which claims to be both a caudal and a co-caudal graph, then it has to be a split graph. If both caudal and co-caudal, then that implies split. The split implies caudal and co-caudal was straightforward, which you quickly could see, but this is more involved. How do you see that if a graph is caudal, any graph which is caudal and its complement is also caudal, then it has to be a split graph, right. So, the point here to note is that suppose a graph is caudal and co-caudal, certain subgraphs are missing, certain induced subgraphs are missing from that graph. If G claims to be caudal and co-caudal, then certain subgraphs, certain induced subgraphs are missing here. Which are the things? Subgraphs missing. For instance, this is missing, right, C4, because it is a caudal graph, C4 cannot be there, induced C4 cannot be there, and C5 is missing. C5 is also, because it is a caudal graph, C4, C5, C6, nothing will be there, but I will say C4 and C5 are missing. And then moreover, because it is a co-caudal graph, that means its complement is a caudal graph, this stuff is missing. This is so called 2K2, is a K2 here, this is a K2. K2 means a complete graph on two vertices, that means an edge. 2K2 means two edges, but just two edges is not enough. This should not be there. Okay, 2K2 induced 2K2, right. If you take that induced subgraph on those four vertices, you should just see two edges, right. Nothing else should be there. That means these four edges should be missing. That is 2K2. Because in our graph G, this 2K2 will not be there. Why? Because if you go to the complement, if this was there, if you go to the complement, you would have seen this, right. This is a C4, and but you are saying that its complement is caudal, because this is a co-caudal graph. So, 2K2 also should be missing. So, we have 2K2 is absent and C4 is absent, C5 is absent, though many other things are also absent. Actually, this captures most of it, because it is from this thing it is obvious that C6 cannot be there. Why? Because if there was a C6, suppose if there was a C6, can you see that we already told it. Why? This is C6, right? Sorry, C7. Yeah, if this is C6, now let me highlight it. See, look at this edge and this edge. What can I tell about it? This is an induced C6. So, therefore, these edges are anyway not present, right. So, therefore, 2K2 also comes along with it, but we already told that 2K2 is missing. So, we do not have to tell that C6 is missing, and similarly for higher cycles. And so, therefore, whatever we told is kind of enough, right. The complement also we can talk about it, right. So, bigger the thing, this 2k2 will take care of it. So, essentially when you say caudal and co-caudal, those three are the things which are important. C4, 2k2, C5. C5 is very special because C5 cannot be captured by the 2k2, because if you can just carefully look at it, see, look, this is not enough here, no, 2k2 will not be coming from this. See, if I take one edge here, no other edge is there. So, suppose if the farthest edge, maybe this one, if I try, see, this connection is there between them, see, this connection is there between them. Or if I try to take this one, but this connection is there, right. So, it is you cannot get induced 2k2 from this C5. C6 onwards you can get, am I right? So, therefore, that is why C5 is specially mentioned, see, C4, C5 and 2k2. Okay. So, when I say that a graph G is caudal and co-caudal, that means its complement is also caudal, then we are sure that it does not have a C4, C5 and 2k2 as in none of these things as induced subgraphs. Induced is important word. You just let me know when I have to stop, okay. I will stop wherever it is to be, because I can, it's time. Huh? So, then of course, this from this thing you have to prove that somehow. You can take it as an exercise that look, if these things are not there, then it has to be a split graph, right.